Okay, guys, today the topic is reflected on the slide. We're discussing limits. As I've said before, I'm not introducing limits here. I'm recapping the idea of limits from what you know from school, and I'm not going to make rigorous definitions, mathematical definitions, but I'm going to try to discuss in such a way that by the time we start differentiation, we're almost at the same level of understanding what is limit, and then we can apply it there to introduce derivatives. Now, so how do we start? I'm going to start this thing this way by looking at these types of functions. This function is f of n equals to 1 over n plus 1, and this one is f of n equal to n over n plus 1. And these are kind of special functions. The domain is the natural numbers. So the n is a natural number. So always, when we're talking about a function whose domain is a natural number, we're going to call that function a sequence. Right, we call these sequences. Let's write that word sequence. In mathematics, a sequence is a function whose domain is a natural number, and in this case it would be something like this. It should be f taking values in n, natural numbers, to real numbers. As you can see here, if I take n equals to 1 for this first function, what I'm going to do to evaluate that, I replace n by 1, I get 1 over 1 plus 1, which is equals to 1 over 2. And you can see this is a real number. It's a rational number, it's a real number, it's not a natural number. So it's actually mapping from taking values of n, assigning them values in the domain, in the real numbers. So such a function is called a sequence. This is a fancy mathematical term. The correct term for what people would say common man's understanding, like in the understanding of my grandmother who never went to school, a sequence is just a queue of numbers. There's a first one, a second one, third one. So there's a first value I can going to assign, a second value I'm going to, first of all, when I take n, 1 is the first one, 2, I assign a second value, that. So if I take 2 here, I think we can see that this is going to be 1 over 2 plus 1, which is equals to 1 over 3. So this is the queue. The first one, the second one, and these numbers, they are called the terms of the sequence, and as you can see, they are real numbers. So I would say the sequence is a queue of real numbers, in simple words. All together. Now, how does the idea of a limit comes into this thing? Let's just make kind of a table here. Let's say we've got n there, then we've got values of n. I don't know what idea you've got from school about what limit is, but I'm trying to just to discuss this thing in such a way that at the end of this discussion we've got a common understanding what a limit is. When we're talking about limit, normally, listen to me, we'll look at limit as the independent variable is approaching a certain value or approaching infinity. And when we are doing that, what we are actually trying to do, we'll try to check what's the behavior of the function, what happens with the value of the function as the independent value is approaching a certain value. Do you understand what I'm saying? In other words, it's a question of analyzing the behavior of the function, the values of the function. The independent variable is independent. You can take any value in the domain. Like for example, we can take 1, 2, 3, 4, and so on towards infinity. I'm not saying infinity is a natural number. I'm just saying the natural numbers grow, they grow indefinitely altogether. So then Here, as you have seen, this is half, and here we're getting 1/3, and there we're going to get 1/4 and 1/5, and so on. But if you look at now this is what I'm saying, when you're looking at the limit, you are, in this case, I'm making my n approach infinity. I want to see what's the behavior of the function as n is approaching infinity. What we can see here, I think you know how to compare rational numbers. Which one is bigger? You might cross multiply, you put the answer there, you cross multiply. Now you take this 3, multiply by this one, you put the number here, you multiply that one, you put the number there. Then you look at the 2 and see which way is the product bigger. Is it this answer this side bigger than that one, or is the answer this side bigger than that one? So I'm getting 3 here, I'm getting 2 there, which means actually half is greater than 1/3. It's true, isn't it? So if you look at this pattern, you see that you are going to get 1/3 less than half, and the 1/4 is actually less than 1/3. Multiply. You get this 4, multiply that side, you get 3. So which means 4 is greater than 3, which means 1/3 is greater than 1/4. So as you can see, these numbers are decreasing. Do you see that they're decreasing? Okay. But one thing which I'm sure of, these numbers are not going to get to 0, but they are decreasing bit by bit. You can go maybe as far as 1,000. You take f of 1,000, you get 1/1000 and 1. And that number is a very, very small number. So what do you think? What is the behavior of this function? What values are the values of the function approaching? I'm saying, what value are the values of the function approaching? 0. So these are approaching 0. I said approaching. I didn't say equals 0. I said approaching. So now, to try to express this kind of phenomena mathematically, this is what we write. We can write now the limit as n is approaching infinity of f of n. We've seen that the values of the function, they approach 0. But now here we put equals 0. We are not saying this f of n is equal to 0. We are saying its limit as n is going to infinity, it is going to approach 0. But mathematically we write it this way. Am I making myself clear? Sorry? To express that English statement, we say the values of f approach 0 as n is approaching infinity. It's summarized this way mathematically. You just read limit of f of n as n going to infinity is equal to 0. So 0 is the limit. 0 is not the values of the function. It is the limit of the values of the function. Am I making myself clear? Oh. Sorry? Is that clear, guys? Okay. Talk to me, man. Talk to me. All right. So that is what's going to happen there. Let's take the second function. And the second function, I think, is more interesting, and it's got many other things which are involved there. I hope I'm going to enrich this discussion as much as possible. We look at this kind of thing. We can do something similar, like a table, but let's not do that. I'll just take particular values and we try collectively to make sense of what is happening to the values of this function as n also is approaching infinity. In other words, as n is growing indefinitely. Right. So if we take 1, for example, 1, we'll have 1 replacing the numerator, then we'll have 1 plus 1. In this case here, n is equals to 1. We get this kind of thing, which is equals to 1/2. When we go to 2, we're going to get 2 over 3. That is when n is equals to 2. Then we must ask ourselves, what has happened from the initial value to this second value? Is the function going up or is going down? In that case, it was decreasing. Now, is it going up or is going down? You just have to check, is 1/2 less than 2/3 or is 2/3 less than 1/2? What's happening? 2/3 is less than half. It's greater. So this is, the function is growing. So we can go to, let's go as far as n is equal to 10. When you get to n is equal to 10, you get this as 10 over 11. You can check again there whether 10 over 11 is greater than all these other numbers there. I think yes, because half of 11 will be somewhere like 5 something over 11, isn't it? But then there's still 1 over 11 to add, so it's more than half. And you can check that that is that. So which looks like these sequences, n is growing, the sequence is also going to grow. But the fact of life, if you look at this, the way the formula is, the denominator is always going to be more than the numerator, yes or no? And then that guarantees that this is always going to be less than 1. But being less than 1 does not stop it from growing. So which means we can say these values approach 1. Do you see what I'm saying? You can check with this, you can go up to big numbers like 99, whatever. You'll see that these values are going to be bigger and bigger, but they'll never get to 1. So summarizing that in a similar fashion, you can say now, limit of f of n, we know which f of n we're talking about now. As n is tending to infinity, we're talking about this one. The limit there is equals to 1. But anyone who looks at this thing will see that this thing is a quite tedious kind of story. Preferable, it would be nice to get a kind of an analytic approach to it and see whether we can compute limits without dealing with these individual values of the functions. All together? Okay. So let's check, let's look at this. If you grab this expression, and they say n is going to infinity, and at the bottom here n is also going to infinity, it more or less says the numerator is approaching infinity, and the denominator is also approaching infinity, which looks like the limit is going to be infinity over infinity. But the problem, this is not a number. You cannot give it as a limit. This is undefined. This entity is an undefined entity. So similarly, if we get something like this, it will be also an undefined entity. So when we're dealing with this kind of undefined entities, we then need some other methods to, especially when we're going to deal with this limit analytical, instead of using particular values like we're doing, we need to do some kind of manipulation algebraical of this expression to get that. So what we're going to do, one strategy is to factorize. Try to factorize and see what happens. Now, how do you factorize this? Let's write limit n approaching infinity, n over n plus that. So our first, at first sight, we see that this thing is going to give us this kind of nonsense. So then we start to say, let's try to do some manipulation and see whether we can sort of bypass that kind of nonsense and get to some kind of a defined limit. So I'm saying the suggestion here is to factorize. Normally when you factorize, you take out a common factor, you choose what you want to make a common factor. In this case, because this expression depends on n, I'll choose to take n as a common factor. In the numerator, I'll have n times 1. In the numerator, if I take out n as a common factor, whenever you take out a number as a common factor, there's some kind of division involved. You cannot take out a common factor without doing some kind of division somewhere, unless if you are doing it in the wrong way. So if I take out the common factor in numerator, I'll divide the first term by n, I'll get 1. I'll divide the second term by n, I'll get 1 over n. And to anyone who is familiar with this kind of thing will see that these two expressions are equivalent. Yes or no? They're equivalent. So what we can do now, we can now simplify that. Some people like to say these things cancel. No, I simplify those things, they simplify to 1. They don't cancel. But it's a language of other people say they cancel. Myself, cancel gives me a very bad idea that once it's cancelled, the whole thing, which is, because this thing is a part of this, the whole thing becomes useless because it's cancelled. But I want to continue working with this thing, so I'm not going to cancel anything. I'm going to simplify things which simplify to 1 or whatever. So I've got that. So I'm now calculating that limit, which is equivalent to what I started with. So what's going to happen there now? You can see there's only one term which involves n. And this takes us actually to the previous discussion there. The denominator was increasing and increasing and increasing, and then the whole fraction shrinks to 0. So similarly, when we look at this, just focusing on 1 over n, sorry for writing upwards there, but I hope it's acceptable because it's not too crowded for anyone not to view. If I now let my n move towards infinity, n approach infinity, which means this denominator is going to increase indefinitely, then the whole fraction is going to approach 0. I never said it's equal to 0. I said approaches 0. But when this part approaches 0, it will actually at some stage be negligible in such a way that this whole rational expression will be, if I may say, dominantly 1. Out of it, more or less 1. So, and then the limit here is 1. Just like we established before, there is 1. This is an analytic approach. What I'm presenting here is an analytic approach, factorizing and then using different facts that we know, and until we conclude that. And the other one there, it was basically the kind of a try and error kind of thing. You evaluate, you check, you evaluate, you check, and all those things. So you must always differentiate between try and error kind of an approach and an analytic method. This one which you are doing there is an analytic method, and that's what we normally use in most of exercises. But the other one, the numerical approach, it actually gave us some kind of intuitive sensing what the limit is, and that is important. But for calculation, fast calculations, we can use an analytic approach. Am I making myself clear? Okay, right. So that being understood now as a limit, now we know that when we are writing something like this, we know exactly what to mean. I hope at this stage now everybody has got an idea of what the limit is. We're looking at the values of the function as the variable is approaching a certain value. Unfortunately, it's approaching infinity. It's not really a value. We're just saying it grows indefinitely. But then we're going to look at when we look at the functions, we're going to look at functions approaching a certain value like 2, 0, 1, whatever. Right. Can we move forward? Okay. With your permission, I'm moving to this situation here. There is a function given. We'll talk about limits and evaluating limits. Let's briefly give an expression for this function. I think it's important, it's going to be useful in our discussion. F of x is a piecewise defined function. As you can see, it's continuous here and it's continuous there. Now it's a piecewisely continuous function. What do I mean by continuous function? Just to recap, I'm not going to give a formal definition again here. The function is continuous when we can draw a graph of the function continuous like that without lifting a pen throughout this domain. That's what it means. Illustrating, I would say that would be enough. But These things have got other formal definitions which can make people's heads turn upside down sometimes, but that is part of the business. So for this function, it's a line. We know the equation of a line, mx plus c. We need m, which is the gradient, which is we run so much and they will rise so much. If we look at this, it looks like we run 2, we rise 2. So the gradient is 1. So the function is x. We need where the function cuts the y-axis, it looks like it's 2. So that's that. That happens where? For x greater or equals to 2. Do you agree? Do you agree, guys? Hello? Do you agree with this? Okay, those who agree, they're not paying attention. It's for greater or equal to 0. The domain starts here. All together? Yeah. I'm just checking whether you guys are here or you are somewhere else. That is greater or equal to 0. For that part of the function you're analyzing there, the domain starts here at 0. What I'm saying again there is that as I'm writing what I'm writing on the board there, you must be paying attention and checking whether I'm writing what I'm saying and that is correct. You mustn't just sit there and then say the teacher is always correct, then everything the teacher writes on the board is correct. Follow the leader until in a big hole. That's an accident. Now let's come to this part of the function. Again, it's a line. And it looks like we pick a point here, run 1, we rise 1, 2, 3, 4. It looks like this gradient is 4. Then this becomes 4x. But it casts the y-axis somewhere there at 1. And then there, we cannot define the function because if we define that 0 equals to this, then if we define it again there, it's going to be 2 values at the same point. So open a circle there and they put a solid dot there. I think we discussed this thing before when we're discussing functions. So then plus the intercept, which is equals to 1. And then this is for x. Can you tell me something? Who is going to complete the sentence? X strictly less than, come again? Less than 0. So that's that. Any questions at that point? No questions. Okay. So now, for this kind of function, like given graphical like this, if we were to analyze limit, let me start by analyzing limit of f of x as x is approaching 0. Limit f of x as x is approaching 0. Now, when we talk of a number line, we've got 2 directions. We can approach a number from the left or from the right. Is that true? We can approach a number decreasing from 100, coming down, approaching 5. Or we can from minus 100, going up, coming to 5. Those are the 2 directions you can approach 5. Yes or no? Yes. Okay. That idea takes us to what we call lateral limits, side limits. What do I mean by that? For us to establish that this function is going to limit at 0, we first of all need to check what happens when we approach that number 0 from the left, and what happens when we approach that number from the right. And that is called lateral limits. Lateral limits. Lado, L-A-D-O, lado, is side. That is in Portuguese, Spanish, and I don't know what other Latin languages. Lado is side. So lateral is from that kind of thing. Lateral meaning side limits. So but the term which is used in mathematics is lateral limits. So what I'm going to do, I'm going to look at a limit as x is approaching 0 from the left first. So I call that side limit from the left, lateral limit from the left. But that is what is done. You cannot just say the limit is this without analyzing first what is the behavior when you're coming from the left, what is the behavior when you're coming from the right. So now let's look at the left side. Let me take another color here and say maybe red is a good color for this one. Let's come here between -1 and 2. We come to this part. The value of the function is somewhere there between 5 and -5 and -4. I come to 1. The value of the function is there at 3. You see what I'm doing? I'm coming closer and closer to 0. I come here. The value of the function is there. I come somewhere here. The value of the function is there. Then I come here at 0 here. The value of the function is 0. After 0, the value of the function is above 0. As you can see, what happens? The value is increasing towards what? What number is here? 1. So we could say that this limit is actually 1. This lateral limit is 1. The side limit there is 1. So as we approach the values of this function, because we're taking these two pieces is one function, but we're looking at this function as we approach from the left, and then the next thing to be looking at the function as we're approaching from the right. So the other lateral limit will be limit of f of x as x is approaching 0 from the right. As you can see also, where I write plus on the right hand side of 0, I write minus on the left hand side. It's just to communicate what we're doing, isn't it? It's from the left or from the right. So let's do that again with the graph illustratively. What's going to happen? Let's come here for 4. It doesn't matter how far we start, as long the direction is towards 0. With that 4, the value looks to be there. The value of function will be maybe 6 there. We come to 3. You can see at 3 we're closer to 0 than we were at 4. Is that true? We come to 2. We come to somewhere between 2 there. You can see the values are decreasing. Do you agree with me? Can you see it? You don't need to understand this one, by the way. What I'm talking about now, you don't need to understand that. You need to see it happening altogether. Then later we use this to understand the other thing. Don't waste your brains then try to understand. You should see. At least see. Can you see that? That the values are decreasing. Let's come somewhere here. We're on the line, we tend towards y. Look where the values. It's close to what? To 2. So we can say now, conclude this by saying, it looks here like these values, the function is going to have a behavior of approaching 2. Then we write limit, lateral limit from the right is 2. Are we together? That's fine. Now, let's leave that as it is there. Let's talk about the same function at a different point. In this case, I'm going to choose the point to be 2. Let's look at the limit of f of x as the x is approaching 2. Now our 2 is here. We don't get to 2, we approach 2. As you write the x approaching 2, we must emphasize that x is different from 2. Even if we don't write it, but in our minds, at the back of our mind, we must have it that x is not 2. Are we together? Okay. So now, let's do that. Let's start from the left. Now, for this part, obviously, the domain starts here at 0. When we are at 0 itself, the function is 2. Let me take that red color again. When we are here, the function is 2. When you get here, the function is that part. When you get at 1, the function is more or less there. What's happening? It's increasing, isn't it? Then when you get here, the function is somewhere there. When you get just close to 2 here, the function is somewhere there. Somebody can tell me that that thing is going up that way. Remember, we're remaining on the left-hand side of 2. The values seem to be going close to 4, isn't it? So what we're doing there, we're talking about the lateral limit. Limit as x is going to 2 from the left of f of x, and our observation, as you see on the graph, it looks like the values are approaching 4. Do you agree? Okay. Now let's come from the left, from the right hand side. Let's come from this direction now. We're coming in this direction towards 2. Now we're coming this one. We can start as far from 4. We go there, there. Then 3, there. Come somewhere here. Let's come here. Can you see that yellow? Okay. Come this there. We're there. We come just below 3. We're there. We come just close to 2 here. We are there. And we are maintaining ourselves on the right of 2. And you can come closer and closer. And you can see that the values are decreasing. But fortunately or unfortunately, they're decreasing towards which value? Towards 4. So we can say there, now we can write there and say limit as x is approaching 2 from the right, limit of what? Of f of x. And say that is equals to 4. What's the difference here and there? The word to use is lateral. What's the difference here at 0 and there at 2? We must use the word lateral. We can answer that question. What's the difference? Comment. I'm asking you to comment. Talk about these limits here when x is approaching 0, and talk about these lateral limits here when x is approaching 2. What can you observe? Nothing. You don't see anything. Yes? Flamin is saying the lateral limits here are different, and the lateral limits here are the same. In other words, the left-hand limit and the right-hand side limit and left-hand side limit are the same. When this happens, when this kind of thing happens, in other words, 1 is different from 2, we say the function f of x has no limit at x equals to 0. In other words, when the lateral limits differ, there's no limit. So the opposite is going to happen here. Here, the lateral limits, they take a common value, then the limit exists. I'll just write here, limit exists. If it exists, what's the limit? The limit is the value of the lateral limits. So in this case, you're going to say here, limit of f of x is x equal to 2. Notice this, check this here. Now when we're writing, giving a final answer here, it's just x turning to 2, and you write it as 4. And this must already carry the message that we established that the lateral limits are equal. And then the limit is there. And this limit, it must be unique. Just like the values of a function at a given value of a function at a given point is unique, the limit also must be unique. Here, the limits are given as 2 different limits from different sides. So there's no unique kind of limit, for lateral limits, then the limit does not exist. Where it's unique like this, we say the limit exists and the limit is equal to that value of lateral limits. Am I making myself clear? Can you tell me, am I making myself clear? Guys, are you understanding what I'm saying? No, if you don't respond and you respond so lazily without energy, it sort of, it gives me a very funny feeling that you don't understand. Maybe you're just saying yes for saying shut up. Is it clear, guys? I mean, relax. I mean, relax. I mean, relax and say, if you don't understand, say, no. I don't understand. With a smile, we'll explain this thing again. All together? Yeah. My job is to explain this kind of nonsense. Fine. Do you understand? Can I hear yes? Okay, that is a forced yes. Okay, I go on anyway because you want it to be like that. Now, what is interesting now about this two, when the limit exists, and at that point the function is continuous, just check something here. Let's take the value of the function at 2. The expression in that domain is this one. It's actually going to be 2, because x is 2, plus 2, and is equals to 4. I think this is one idea which you should have gathered at school, that when a function is continuous and you are calculating a limit around the point, that limit is going to be equal to the value of the function. What I'm saying here, in this case, if the function is continuous at a, then the limit of the function as x is approaching a, limit of f of x as is going to be equal to the f of a. That's what happens normally when the function is continuous. Are we together? Okay. Now, I think we are ready to pass to another stage now. Now, I'm inviting every one of you, don't worry about the expression of this function, but I want you to establish whether the limit exists as x, only whether it exists. I'm not interested in the limit, I'm just interested in knowing whether the limit exists as f is tending to 0. You analyze the graph like we did before. I'm giving you 2 minutes to do that. I think I've given you more than 2 minutes as I promised. So now I think I'm expecting results here. What can you say? This limit, can you say it exists or it doesn't exist? It exists. So this limit exists. And now, if you say it exists, you must establish that the lateral limits are equal. Isn't it? What are the lateral limits then? So in this case, you are saying limit of f of x as x is approaching 0 from the left is equal to the limit as x is approaching 0 from the light, and we are saying that is equal to what? Can you tell me? That will equal to what? 1. Is anyone got a problem with that? This is just analysis done graphically. I think you agree with us. You can agree with this. If for those guys who are silent, there's always going to be 1 or 2 guys who are never going to say they understand or don't understand. But to help them, we're just going to illustrate it for those type of guys. At 4, we start at 4, we come here, the values are going to be there. That is from the right. We come there, it looks like the values are decreasing. We come there, we come here, we come there, we come there. You can come, there are infinite numbers more there. You can see the values seem to be approaching 1 from the left. From the right, sorry. We come from this left-hand side. We can start from there as far as -5. We go there, we go to -4. We're coming there. Looks like something is happening. Something is happening. So the values are going down and they seem to be approaching this value here 1 altogether. Then we establish that this limit is what the lateral term equal to 1. So once the lateral limits are coinciding like that, then we can comfortably write here that therefore limit of f of x as x is approaching 0 is equals to 1. I repeat, no one said f of x is equal to 1. It's a limit of f of x is equal to 1. In other words, the values of f of x approach 1. No one said the values of f. But if the function is continuous, like I said before, the values of the function will coincide with the value of the limit. Okay, so this is what we're going to discuss here. There it is. Now, here I'm just going to recap what is a polynomial. I think a polynomial, you know, all of us, is an expression of this nature. A n x to the power n. N, these a n are just coefficients which I'm just numbering. Plus a n minus 1 x to the power n minus 1. Plus dash 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 plus a 1 x plus a 0. That's a polynomial. So any of these coefficients can be 0, then we remain with fewer terms. But at the moment, I think there are n plus 1 terms here. N plus 1 terms. But if it happens that a1 is 0, that's not a problem. Like now, if we're looking at this line, it's a binomial, but I can say it's a polynomial whose other coefficients are 0. So then it's only giving us this part of the polynomial, which gives us a line. Now you will see that then if we try to check the limit, let's calculate limit of f of x as x is going to 1. We'll check the lateral limits like we did. We're approaching 1 from this side and we're approaching 1 from this side. Whilst we're doing that, we are not touching 1, we're just looking at the behavior as we approach 1. I think you can see that from 3 there, to go down, down, down. Let me just draw the lines for people to be convinced. Let's say from 3 there, it will be 3 times 2 plus 1, it will be somewhere there, 7. We go down there, the values are going to be there. You go down here, the values are going to be there. Remember, we're approaching 1 from the right. The values are going to be there. You can see that these values are decreasing towards 3. Now, if you come from the left, you can start from minus 4 or minus 3. You come here, the value is there. It's 4, minus 4. You come at minus 2, you come into, sorry, somewhere there. You come there, there. Until you get to 0, it's there. You come here, now the values are there. You come closer, the values are there. You come close, 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 close. You can see the values are there. Keeping to the left, you can see also there's a one common value they were approaching, isn't it? So you can say the value, the limit there, the lateral limits are equal and they're both equals to 3. But if you now take f of x as 2x plus 1 and evaluate it at that point where you are calculating limit, and you are getting 2 times 1 plus 1, and you can see that that is equals to 3. So that's where I'm saying, if a function is continuous at that point or in this domain or calculating limit, always the value of the function at that point and the value of the limit at that same point, they are going to coincide. That fact is very, very important. If ever you've done limits at any level, primary school, tertiary, whatever, I think you can forget everything else and remain with the fact that whenever the function is continuous at a point, and want the value of the limit at that point, the value of the limit is the value of the function. And that simplifies a lot of things. And with polynomials are nice functions. They're always defined. You will not get anything like infinity over infinity. You will not get anything like 0 over 0. I'm talking about polynomials. So the values of the function, the values of limit are always going to be easily computed by evaluating the polynomial itself. Are we together, guys? Do you understand what I'm saying? So for a polynomial like this, then we can always say limit as x is approaching a value a. What is the domain of a polynomial? The real numbers. What is a? I don't mind what a, as long as a is a real number. So the value of the limit of a polynomial as x is approaching a in the domain of a polynomial, which is all real numbers, and the polynomial non-continuous, then this is always going to be p of a. That is that. Any question? Any question? No question. Now, so obvious, when you look at polynomials, from polynomials you can look at rational expressions. You need also to calculate their limits and so on. But whenever you look at rational expressions, it will be very, very careful. You must be very, very careful to check what happens, especially with the denominator. The limit can exist, that of the denominator, and it can be 0. But when that denominator is in a rational kind of situation, then the rational expression will not have a limit because you cannot divide by 0. You understand? Then there again comes the situation, what do we do with such kind of things? What kind of techniques can you apply to calculate limit? Again, there we are going to look at possibility of factorizing and trying to evade an undefined situation. So I'll take on examples like that just for a few minutes. So for the situation of, let's say, we said polynomials are easy. Like I've said, you just evaluate the polynomial, you get the limit. Now let's briefly look or recall what we were supposed to do with rational functions. Let's say we've got the given expression like this. Maybe somebody can say, okay, let's calculate the limit of f of x as x is approaching -2. Like I said, if you have got such kind of situation, you should check that if I evaluate the limit directly, do I get an undefined situation or not? But in this case, I think no. Check what's happened. If a limit is approaching 2, there's no undefined situation. So what we can do, we can actually plug into the expression and they calculate the limit. In this case, we're going to say -2 squared minus 4 over -2 minus 2. That will be the limit. Then in this case it will be 4 minus 4 over -4, which is 0 in numerator. Then we can say the limit is 0. That's not a problem. But in the case, if we were to analyze the behavior of this function as x is approaching 2, then let's say we're getting the limit for this. So at first glance, we can see, oh, in the denominator we're going to have a problem. We're going to have maybe a defined entity somewhere there over a 0. But the first commandment says, thou shalt not divide by 0. So this is not going to be acceptable as the limit of it. So the question is, how do you normally organize a bypass of this kind of undefined situation? Is via factorization. That's one of the strategies. So now you can say, now this is same thing as limit x approaching 2. You factorize, in this case, the numerator as that. So as you can see, remember when we're looking at limit here, at the limit, we see it emphasize the fact that this x is not equals to 2. So we cannot have this kind of thing 0 over 0. So but that situation is equivalent. If we factorize now, we can now see that we can simplify this factor to 1. Then it looks like we're calculating a limit as x approaching 2 of x plus 2. Now when we're in this situation, we're in a simple situation where there's no undefined. Then we just plug in the value 2 and we get that our limit is equals to 4. All together. You can also go and try to do this thing numerically. If you take values of this expression outside 2, around 2, you will see definitely that they will approach 4, which will suggest that these values are approaching something. But analytically, how do you get that limit without valuing numerically? This is how we do it. We evade that kind of situation, 0 over something over 0, by doing some kind of factorization. Altogether, as you saw before, when we were approaching infinity with that sequence, we also did some kind of factorization to avoid the undefined situation of infinity over infinity. So that is a strategy which you must keep in mind. Once you, at first glance, you see that your limit is giving some kind of undefined 0 over 0, infinity over infinity, you must try to say, can I factorize? Can I do some kind of algebraic manipulation to evade this kind of a thing? Then, if you do it successfully, you'll get some kind like that. Is it clear, guys? Sorry? Yeah. Like I said, I'm not really presenting a chapter on limits or what. I'm trying to recap what you know on limits, or maybe what you've forgotten limits. So that when we start our new chapter on differentiation, we are more or less on the same page. We share the terminology, limits, approaches, undefined expression. We sort of share it, because sometimes it's very, very difficult to just jump into the chapter, start teaching, you discover that the one guy, he once met limits. Now you're talking about limits. He feels like you're speaking Chinese to him without ever learned the language, Chinese language or Greek language. That's a big problem. So my encouragement to you guys now is that if ever these things were rusting or fading away, in just about how many months? 3 months. January, February, March. This is April. I suppose you wrote your exams in December. Things can fade so quickly because our memory is not very good. But then this serves as a recap for you. I think it serves the purpose. If it doesn't serve the purpose, then I'm very sorry for doing something useless. All together. Right. So let's move forward a bit. Now, what I want to discuss with you, I want to talk about what we can refer as special limits. You know, special limits is kind of those things which I can say also, learn everything, forget everything, but you must remain with something. You must remain with something. These are things which must always remain behind. Special limits, because they're useful in several chapters also. So one special limit which I'm going to ask you to investigate, and I want you to come back to me and tell me, what did you get? I don't think you had the experience of this thing at school, but I want you to get it, then it will help me somewhere when we're discussing this chapter, the next chapter, to do this thing. Take this expression and evaluate it for several n. N is natural number here. From 1, 2, 3, 4. You just get 1 plus 1 over n. You can use a calculator and then elevate it, write it down. Next thing, elevate it, write it down. Next thing, elevate it. If you are very observant, you will see that this will lead you to a number which we have already discussed. So my task to you is to try to find out which number is that. And also, associated with this thing, which is going to help us somewhere, I think we're going to have an expression like this. 1 plus x then this somehow is going to help us, understanding of this limit is going to help us that, and that is going to take us somewhere where it's going to be very, very important. Now, which limit do you want to discuss at the moment? I want to have a function here, which is x over sine of x over x. And I want the limit of this function as x is tending to 0. Now, what I'm going to do here, I'm not going to do a rigorous proof of what this limit is, but I'm going to discuss with you and using some illustrations in such a way that at the end of discussion you must have a good feel, a good understanding of what that limit, this limit is A or is B or is what. Do you understand what I'm saying? Okay, so let me just organize a diagram here for this. Okay guys, I've organized a diagram there. So this line here is y equals to x. Let's say this is y equals to x. Please don't lose sight of what we're trying to do here. We're trying to understand what is the limit of this function as x is tending to 0. So maybe let's write that now here and say limit as x is going to 0 of sine of x over x. Want to establish what this is equals to. Now, obviously this is a rough sketch, but I hope we're going to get something from this rough sketch. Let's start from somewhere here. There. Let me maybe use another color there. I take a value of this function and I take a value of sine. It's somewhere there, less than 1. And this one is 4, somewhere there. Now if I divide those values, I'm actually dividing a number whose absolute value is less than 1 by a big number. What's going to happen? The value is going to be almost 0. You understand what I'm saying? This will happen if I take a similar kind of portion this side. Because this side, actually, there, the sign is negative. There, for this graph, it will be already positive. It's what you get here in negative value. And what you're going to get here is negative value because it will be sine positive divided by this line, the value of line negative. Both sides, that's minus 4 and plus 4. I'm going to get a very small negative number. Now, if I come closer, let's say here, the sign is still very small, but the denominator is a little bit smaller. Maybe there's still not a difference, but let's come here. If you look at the values of sine here and the values of line, the difference is bigger. What are they here? They are nearer to each other, isn't it? If you divide there, I think you expect the absolute value of that number to be this one, to be bigger than that one. Because the difference, the denominator is very big, the numerator is very small. But here the numerator and the denominator are closer. I think you must expect a number which is a bit higher. Still less than 1 because the denominator is bigger, but a bit higher than this one. Then we come here. Now, as I'm going towards 0 here, you must also be trying to reflect what's happening this side. Like exactly, if we're at minus 2 there, let's take it minus 2. I'm coming here in minus 2, I'm going there. Look, sign is positive, the line is positive, I divide, but these things are now closer to each other. When I come here at minus 2, same thing. Sign is negative, the line is negative, which means the answer is going to be positive. Negative divided by negative, answer positive. But they are closer to each other as compared to there. So as I come closer and closer, as you can see also from the graph, as I come closer and closer to zero, somewhere here to zero, it looks like the graph of the sine and the graph of the cosine are almost equal, isn't it? So though the sine is still less than the line, but they are almost equal. Now if you divide two numbers which are almost equal, here there are two numbers which are almost equal, both negative. And this side there are two numbers which are both almost equal, both positive. What will be the answer? Not 1. Almost equals to 1, isn't it? So as you go closer to 0, this ratio is going to grow towards 1. Then from that kind of understanding, we understand that this limit here is equals to 1. That's a special limit. This is what I'm saying, that this kind of limit you must never forget. And I can tell you from experience, if you go to Maths 4 or Signal Processing 4, you will get this thing applied in a way that if you have forgotten about it, you will actually think the guy who's talking to you in front of you is mad. But you're just applying this thing. Please guys, don't blame people for some things. I told somebody yesterday that if you find yourself in a mistake today, in a mistake tomorrow, maybe with other people or whatever, you must start asking yourself, what is your percentage contribution to that kind of problem you are having with people? It might be that there's a heap pile sources of problems with you. So this thing will be applied in such a way that people will assume that you know it. The fact that you've forgotten it doesn't matter to any other person. It will all depend on you. So I'm giving you a warning. I'm talking from experience. You go to Signal Processing 4, Mathematics 4 without this thing. You will feel that some part of the course is a torture because you've forgotten these small things. So that's what I'm saying. These things are building blocks. You must never forget them. Are we together, guys? Okay. So let me just pause there for a while. I want to do something. Okay, guys. So this is I'm just going to stop here and say this is the special limit. Like I said, please try by all means that you don't forget this kind of thing. Now, what I can do is, especially for those people who think their skills of computing limit are rusting, like, please go to your books. Even if it's a grade 12 book, there's nothing called grade 12 maths. Maths is maths. Get that book, revise anything you can revise there which is valuable for limits. You get something like this, then you know. Because, why am I emphasizing that? Because at the end of the day, when we're going to talk about, I said we're going to talk about derivatives. A derivative, you will see, it will actually more or less, or I don't know what I can say, but a derivative, it will end up being a limit anyway. But what you can, like I'm saying, a derivative is a limit. The only question you can ask, of what? That's what we're going to look at. All together. So your skills and techniques of calculating limits are important. So please go and revise. For now, for this one, I'll just say thank you for listening, and I hope I didn't annoy anyone with my kind of funny comments. Good luck for the rest of the day.